Okay, so we'll cover the building blocks, yeah. Limits, derivatives, integrals. Then maybe look at where students tend to get tripped up.
Definitely. And critically, how to actually learn this stuff effectively. It's not just about sitting in lectures. It's got to be more active than that, especially at the college level.
Sounds like a plan. Where should we start? The absolute basics.
Let's. So calculus, at its heart, is really the mathematics of continuous change. That's the core idea from one of your sources. Think smooth changes, nothing abrupt.
Okay, continuous change. And it splits into two main areas, right?
Exactly. You've got differential calculus and integral calculus.
Differential is the speed right now, the slope at this exact point.
You got it. Instantaneous rates of change. Like, yeah, the precise speed of something at one moment or the steepness of a hill right where you're standing.
Okay, and integral calculus.
That's about accumulation. So how much distance did that thing cover over time?
Yeah.
Or what's the total area under that curve, the total volume of that hill?
Got it. So for differential calculus, the big word is derivative.
That's the one. The derivative is that instantaneous rate of change. Geometrically, picture a curve and then a line that just kisses the curve at one point. That's the tangent line. The derivative gives you the slope of that line.
Okay, the slope of the tangent line. How's it actually defined, though? You mentioned limits.
Yes, exactly. The formal definition uses a limit. Think about taking 2 points on your curve and drawing a line between them. That line's slope is an average rate of change.
Okay.
Now, imagine sliding those 2 points closer and closer together, infinitely close. The derivative is the limit of the slope of that connecting line as the points basically merge.
Okay. So it's like zooming in incredibly close to see the direction at that single point.
That's a great way to put it, like using a mathematical microscope.
So how do we, calculate these derivatives without always drawing points?
Right, that's where the rules come in, the differentiation rules. There's the power rule, which is super common for things like x squared or x cubed. Then you've got rules for adding, subtracting, or multiplying by constants. The sum, difference, and constant multiple rules. Pretty straightforward.
Okay.
And then the slightly trickier ones. The product rule for multiplying two functions and the quotient rule for dividing them.
Yeah, I remember those needing careful application.
They do. But mastering these rules and knowing how to combine them, like one of your sources points out, is absolutely crucial. It's your toolkit for the whole course, really.
Okay, toolkit acquired, but let's circle back to limits. You said derivatives are built on them.
They are. Limits are the absolute foundation. A derivative is a specific type of limit. A limit basically asks, what value does a function's output approach as its input gets super, super close to a certain number?
So the function might not even reach that value or might not be defined there, but the limit tells us where it's heading.
Precisely. Think of it like guiding a rocket towards a target.
Yeah.
Even if there's a small blip right at the target, the limit tells you the trajectory it was on just before it got there.
Okay, that helps. What about that epsilon delta stuff? Is that important to grasp?
The formal definition, it's rigorous. Basically, epsilon is how close you want your function's output to get to the limit value. Delta is how close your input needs to get to its target value to guarantee you land within that epsilon range.
So delta depends on epsilon. You pick how close you want to be, and the definition tells you how precise your input needs to be.
You've got it. Make 5 close as we want to $. By making sufficiently close to $1. That's the essence.
Okay. And there are different kinds of limits, too.
Yeah. You have one-sided limits approaching a point from just the left or just the right. For a regular limit to exist, the left-hand limit and the right-hand limit have to meet at the same value.
Makes sense. Like approaching a door from either side, you have to end up at the same door.
Exactly. And then there are limits at infinity. Those tell us about the function's long-term behavior, what happens way out on the graph as x gets huge, positive or negative. Like, does it level off?
Okay. And calculating limits. If sometimes you can't just plug the number in, right? Like you get 0 divided by 0.
The dreaded indeterminate forms,
Yeah.
Yes. That's where algebra comes to the rescue. You often need to manipulate the expression factor, multiply by a conjugate, use trig identities to cancel out the part that's causing the 0 over 0 problem.
So algebra skills are still super important here.
Absolutely essential. Your sources had good examples with trig limits, like limx to fraction 3x. You can't just plug in 0. But using that known limit, limx to fraction, and some clever manipulation, you can find the answer.
Okay, got it. Algebra first, then evaluate the limit. So that covers the derivative side pretty well. What about the other branch integration?
Right, integral calculus, accumulation. The main concept here is the definite integral. Geometrically, think of the area trapped between a function's curve and the x-axis over a certain interval, say from xa to xb.
Area under the curve. Seems simple enough.
Well, there's a slight twist. It's the signed area, or the algebraic sum of areas. Area above the x-axis counts as positive, but area below the x-axis counts as negative.
Oh, okay, so it's like net change. Positive contributions and negative contributions.
Exactly, like tracking your bank balance deposits are positive area, withdrawals are negative area. The definite integral gives you the final net balance over that period.
Interesting. How do we find that exact area then? It's not always simple shapes.
The rigorous way is the Riemann sum. You slice the area under the curve into tons of really thin rectangles. Calculate the area of each rectangle, height times width, and add them all up.
Okay, that sounds like an approximation.
It is, initially, but the definite integral is defined as the limit of that sum as you make the rectangles infinitely thin, and therefore use infinitely many of them. That funny elongated S symbol for integration actually comes from S for summation. It's a reminder of adding up all those tiny pieces.
Wow, okay. From adding rectangles to an exact value via a limit. That's pretty neat.
It is. But calculating those limits of sums directly can be, well, a nightmare.
I bet. So there must be a better way.
There is. And it's probably the most important theorem in calculus, the fundamental theorem of calculus.
Sounds important. What does it say?
It establishes this incredible, beautiful connection between differentiation and integration. It basically says they are inverse operations, like addition and subtraction or multiplication and division.
Inverse operations. So finding an integral is like undoing a derivative.
Precisely. The theorem gives us a way to calculate a definite integral, that area, by finding an antiderivative of function whose derivative is the function we started with and just evaluating it at the endpoints of our interval.
So instead of the complicated Riemann sum limit, we just find the antiderivative and plug in the endpoints.
Exactly. It's a massive shortcut. A total game changer discovered by Newton and Leibniz. It connects the rate of change idea directly to the accumulation idea.
Okay, that is fundamental. So mastering derivatives helps with integrals too, because you need to recognize antiderivatives.
Absolutely. They're two sides of the same coin.
All right, that's a great refresher on the core concepts. Now, thinking about me, coming back after 15 years, I really want to avoid common mistakes. What are the typical places students get stuck?
Yes. The pitfalls. Your Reddit source, drawing from actual teaching experience, flagged quite a few common ones. With limits, for instance, just notationally, confusing limits to d, approaching c from the left, with limits t to d, approaching negative c, totally different ideas.
Oh, yeah, I can see that happening. That little minus sign's position is critical.
It really is. Another big one, when a question specifically says, use the definition of the derivative, that limit of the difference quotient.
Yeah.
Students will sometimes just use the power rule or other shortcut rules. You have to show the limit process when asked for the definition. It shows, understand the foundation.
Okay, read the question carefully. Don't jump to shortcuts if the definition is requested.
Exactly. And even in the difference quotient, little algebra mistakes are killers. Writing 5x plus $h instead of the correct 5x plus $h, that throws everything off.
Right. Got to substitute sex color plus h into the function correctly. Small detail, big impact. What about using the derivative?
Finding the tangent line slope. A common error is using the derivative function, say 5x teller, as the slope before plugging in the specific x value of the point you care about. Remember, false step x gives the slope formula. You need 5x for the slope at 6 step x.
So find the derivative function first, then evaluate it at the point. Got it.
And then distinguishing between the derivative value, the slope, and the equation of the tangent line itself, y1x equal to mx by 1, 1. They are related, but they're not the same thing.
Right. One's a number, the slope. The other's an equation of line.
Exactly. And finally, notation, especially phrasing of A versus vertexes.
What's the key difference there?
Friday D is the derivative of y with respect to x. It's a result. Friday D is the operator. It's the instruction telling you to take the derivative of whatever comes next. Using them interchangeably is a big no-no. That story about the student using filer like a command prefix really drives that home.
Wow. Okay, those are definitely things to watch out for. Thanks. So knowing the concepts and the pitfalls is one thing, but actually learning it, especially after a long break, what strategies work best?
Well, a key theme across your sources is that learning calculus, really any college subject, isn't passive. You can't just absorb it from lectures. It has to be an active, ongoing process.
Active meaning?
Meaning lots of practice, engaging with the ideas, trying to solve problems yourself. It connects to general STEM skills like inquiry and problem solving. It's about doing, not just listening.
Okay. And what does college-level practice look like for calculus?
Good question. One source talks about sustained engagement, complexity, independence, and authentic application. For calculus, that boils down significantly to really digging into problem sets.
Ah, the homework.
Yep. Seriously. Multiple sources stress this. Don't just go through the motions. Really wrestle with the problems. Try them independently first. That's where the real learning happens. It forces you to apply the rules, connect the concepts.
So no skipping the problem sets or just looking up answers?
Definitely not if you want to ace it. And think about deliberate practice. Focus on the types of problems you find hard. Don't just keep doing the easy ones.
Makes sense. Target the weaknesses.
Exactly. And working with others can be huge. Form a study group. Explaining concepts to someone else or hearing their explanation can really solidify things. Your sources mention collaboration and scaffolding, building up complexity together.
Okay, study group, good idea. Anything else?
Reflective practice. This sounds a bit abstract, but it's powerful. Take time to think about how you're studying, what's working, what isn't. Are you understanding why a method works or just memorizing steps? Adjust your approach based on that reflection.
Huh. Meta-learning almost. Thinking about the learning itself.
You got it. And hey, don't discount resources like Calculus for Dummies. Sometimes a simpler, more intuitive explanation can unlock a concept that the textbook makes seem overly complicated. It could be a great starting point or supplement.
Good tip. Use all available tools. Okay, this is super helpful. We've got fundamentals, pitfalls, strategies. Now, you mentioned differential equations earlier. How does that fit in? Is that like the next step?
It often is, yeah. Differential equations are basically equations that involve a function and its derivatives. Remember how derivatives describe rates of change? Differential equations set up relationships where the rate of change depends on the function's value itself, or time, or other things. They let you model how systems change.
Model real-world stuff.
Exactly. Your notes listed tons of examples. Springs bouncing, pendulums swinging, electrical circuits, population growth, economic models, even fundamental physics like ultramagnetism or fluid flow. It's incredibly powerful for describing the world mathematically.
Wow. Okay, so calculus is the language you need before you can write those models.
Precisely. One source explicitly mentioned calculus and real analysis as the necessary background. You need that solid grasp of derivatives and integrals to even start tackling differential equations. They're built directly on calculus concepts.
And these equations have different types, too.
Yeah, they get classified. Ordinary differential equations, ODEs, have just one independent variable, usually time. Partial differential equations, PDEs, have more than one. They're also classified by order, based on the highest derivative in the equation and whether they're linear or nonlinear, which affects how you solve them.
Fascinating. It really shows where mastering calculus can lead.
It really does. It opens doors to modeling complex systems in almost any scientific or engineering field. So that effort you put into nailing calculus now, it pays off later, big time.
Okay, so bringing this all together. For someone like me, returning after 15 years, wanting to ace calculus, it's not about magic bullets or just memorizing formulas.
Not at all. It's about active engagement.
Right.
Really understanding those core ideas limits are the foundation, derivatives measure change, integrals measure accumulation, and the fundamental theorem ties them together.
And being super careful about those common mistakes. We talk about the notation, the definitions, the algebra details.
Absolutely. Vigilance there is key. And then adopting those active learning strategies. Consistent, deliberate practice on problem sets, working with others, reflecting on what works for you.
It's about building that deeper, more flexible understanding, not just surface knowledge.
Exactly. Cultivating that calculus mindset. Seeing the world in terms of change and accumulation, it's a way of thinking that honestly will help you way beyond just this one course.
This has been incredibly helpful. Seriously, I feel much more prepared. Like I actually have a roadmap now. Thank you.
You're very welcome. It's an exciting challenge you're taking on.